We're going to evaluate the following three limits. So start with the top limit. Limit as x approaches -4 of the rational expression x squared plus 5x plus 4 over x squared plus 3x minus 4. The issue with this limit is that even though we have this rational expression, if you plug in x equals -4 into denominator, you will see that when x is -4, denominator vanishes. So if we try to evaluate this limit by direct substitution, we see that the rational expression doesn't exist at -4, so we're going to have to do some work. The work, in this case, amounts to factoring and hopefully cancelling some common terms that cause trouble. So if we factor the expression in numerator, we're going to have x plus 4 times x plus 1. If we factor a denominator, we're going to have x plus 4 times x minus 1. So now we see that x plus 4 cancels out in numerator and denominator, and we're left with the limit as x approaches -4 of x plus 1 over x minus 1. And in this form of the limit, in this form of rational expression, if we plug in x equals -4, we don't have a division by 0 problem. We're actually going to have -4 plus 1 divided by -4 minus 1, which is -3 over -5, which is the same as 3 over 5. Okay, and that's actually the end of the calculation. So the original limit is equal to 3/5. So moving on to this limit. In this limit, we see that we're trying to do the limit as x approaches -3 of the expression 1/3 plus 1 over x, all of that divided by 3 plus x, and it's the similar problem. When x is exactly -3, 3 plus x vanishes. So to simplify this expression, we're gonna do the following. So the two fractions in numerator have the common denominator of 3x. So I'm gonna multiply both in numerator and denominator by 3x. And we're going to simplify numerator so that it eventually flattens out, and we're going to keep denominator as it is. So in numerator, we distribute 3x, we're going to get 1/3 times 3x plus 1 over x times 3x. Denominator, we're going to keep the same. And then in numerator, so we cancel 3 and 3 in the top left term, x and x in the top right term, so that we're left with x plus 3 in numerator. And then denominator is 3 plus x times 3x. So now we know that x plus 3 is the same as 3 plus x, so we get to cancel them. There is positive 1 left as a factor in numerator, and the limit is the limit as x approaches -3 of expression 1 over 3x. And now, when x is -3, this expression doesn't have any division by 0 problem. So we end up having, for the final answer, -1 over 9. That's the value of the limit. And so now we can look on the last limit. So it's limit as t approaches 0, expression 1 over t minus 1 over t squared plus t. And what we will do common denominator, and we're going to combine the two fractions into a single fraction. So, but before we do that, we observe that the second fraction allows us to factor out t, so that the second denominator is t times t plus 1. So the first fraction is missing a factor of t plus 1. So after we multiply the first fraction by t plus 1, we have the difference of those two fractions. Now they have common denominator. So we get to do the difference, so it's difference of numerators over the same denominator. So we have the expression t plus 1 minus 1, and plus 1 and minus 1 cancel out. So we eventually left with limit as t approaches 0 of expression t divided by t times t plus 1. And now we see that we can easily cancel t in numerator and denominator, so that we left with a limit as t approaches 0 of 1 over t plus 1. So this expression finally doesn't have any division by 0 problem. So if you plug in t equals 0, you safely get 1. And that's the value of this limit. We're going to evaluate the following 3 limits, and we're essentially going to use a very similar approach to each of those 3 limits. We're going to try to factor and cancel any factors that prevent the easy calculation of the limit. If we start with the top limit, we have limit as x approaches -2 of expression x cubed plus 8 over x squared minus 4. So the problem is that the expression in denominator is exactly 0 when x is exactly -2. So we're going to try to factor and cancel something that prevents the direct calculation. So we start by observing that 8 is the same as 2 to the 3rd power, and 4 in the bottom right is the same as 2 squared. So we get to use the factorization formulas. So in numerator we have the sum of the cubes, so that splits into x plus 2 times x squared minus 2x plus 2 squared. So it's the a cubed plus b cubed equals a plus b times a squared minus ab plus b squared formula. And downstairs we have difference of squares, so that factors into x minus 2 times x plus 2. And after the factorization, you see that x plus 2 could be cancelled, so that we really have the limit as x approaches -2 of expression x squared minus 2x plus 4 over x minus 2. And this form of the expression allows us to plug in x equals -2, and we don't have any division by 0 problem. We end up having an answer of -3 for the limit. The next 2 limits, they obviously have division by 0 problem, since we have h approaching 0. So our ultimate goal would be to work on the expression in numerator so that eventually we're able to cancel h. So we're going to take the route of recognizing that 25 is the same as 5 squared. So we again have a difference of squares in numerator. And we're going to use the similar a squared minus b squared formula. So in this case, a is going to be 5 plus h, b is going to be 5. So a plus b is, a minus b is here, and a plus b is there. Okay, and simplifying this slightly further, we have 5 plus h minus 5, and then we have 5 plus h plus 5. So in here, we have this, and since 5 plus h minus 5 simplifies to be just h, and then 5 plus h plus 5 simplifies to be 10 plus h. Okay, and now we have h as a factor in numerator, so we get to cancel it with h in denominator, and we're left with the limit as h approaches 0 of expression 10 plus h, and that gives us 10 without any trouble. So the answer to second limit will be positive 10. And with the third limit, we take a similar approach, but this time we use the fact that 8 is the same as 2 cubed, and we have a difference of cubes here. So, and difference of cubes factors into a minus b times a squared plus ab plus b squared. So this is a minus b. This is a squared, this is b times a, and this is b squared. And this expression, 2 plus h minus 2, this is what simplifies to 2 plus h minus 2, and then 2 and -2 will disappear. Okay, so we have limit as h approaches 0 of h times this whole mess divided by h, And this is where we get to cancel h, and we're looking at the limit of this nice expression. So now we get to plug in h equals 0, since we just eliminated the problem of division by 0. And we have the following answer. It looks like we get 12 when we're done with all the cancellations. We're going to evaluate this limit as h approaches 0, of the fraction 1 plus h to the 4th power minus 1 over h. And the problem is that this limit calls for division by h, and when h is exactly 0, we have division by 0. So what we're going to do, we're going to work on making the numerator look like the difference of squares. 1 is the same as 1 squared, and then we're going to represent the 4th power as the second power of something else. And so the 4th power is going to be the second power of a square. So we just need to have 1 plus h squared in there. And so we have something squared minus something else squared. So we're going to split it into a minus b times a plus b expression. So the role of a is going to be this 1 plus h squared expression. That's what we're going to play the role of a, and b is going to be just positive 1. So we have this limit as h approaches 0, 1 plus h squared minus 1 times 1 plus h squared plus 1. And the second parenthesis, 1 plus h squared plus 1, is not factorable. But the third parenthesis, 1 plus h squared minus 1, is actually factorable further. We again represent this one as 1 squared, and we again have difference of squares. Okay, so do the similar a minus b times a plus b trick. And we're going to be looking on limit, and we have 1 plus h minus 1 times 1 plus h plus 1 times the familiar 1 plus h squared plus 1 term, and all of that over h. So what happens, we remove unnecessary parentheses, and we have 1 plus h minus 1, which 1 and minus 1 cancel, and 1 plus h plus 1 becomes 2 plus h. Okay? And after all of this factorization, we see that we get to cancel h in numerator and denominator. So that denominator becomes just 1. And we really have the limit as h approaches 0 of expression 2 plus h times the expression 1 plus h squared plus 1. So now we can easily plug in h equals 0, and we end up having the limit to be 2 times 2, which is exactly positive 4.